and welcome to Unapologetically Technical. This is the show that's different. We go deep. We go all the way down. This is in this show we're going to be talking about all sorts of deep technical things. And with me today is Semih Salihoglu. I said that right. He is an associate professor at the University of Waterloo and the co-founder and CEO of Kuzu. Welcome to the show, Semih. Would you mind introducing yourself a bit more?
Yeah, thank you very much for having me, Jesse. So my name is Semih. I'm an associate professor in the computer science department at University of Waterloo, and also one of the co-founders and CEO of Kuzu, which is a spin-off graph database company from my research group. So what else do you want me to say? That's briefly who I am.
Well, I guess the other thing we were just talking about before is you're from Turkey. And so we were talking about your trip to Turkey. And so if somebody wanted to go to Turkey, what's the place that they should go to?
They should certainly start in Istanbul. Istanbul is an amazing place. Yeah, so it is right. I am from Turkey. I grew up, I was born and raised there until college years. Then since then, I've been living in North America for a while in the United States, and then for the last 9 years in Canada. So Istanbul is certainly the place to go. It's a major city. It used to be the capital of Rome, and then the capital of the Ottoman Empire. I'm in love with that city, and so that's the place to start for sure, or spend a long time. And then a lot of people do the Mediterranean, so like Western and Southwestern Turkey, and is very similar to like Greece. So it's the Mediterranean sort of experience you'll get there. And then there is the southeastern parts where you're getting closer to Mesopotamia, basically Iraq, Syria, and they've got a different feel over there. So those are the three parts that I would highly recommend visiting.
So I've been to Istanbul and I loved it. I walked all through the bazaar. I went through every single nook and cranny of the Grand Bazaar. It was fun. And I went to the various mosques and saw the various relics that they had. That was interesting. But one thing I didn't know about was Turkish breakfast. I didn't know that Turkish breakfast was a thing, that I should have tried it. What is Turkish breakfast?
So Turkish breakfast is certainly the most important meal of the day for Turks. It's a big deal. So it's the base of it is this white cheese and tomatoes and olives, the black olives usually, or green olives. You got our own kind of either bread, or we got our own bagel like thing called simit. So that's very kind of the core of it. But usually it's like people like sitting it down and having like long breakfasts, certainly on the weekend. So in my family, for example, that's what we do. Like the family gathering is that Sunday morning breakfast, which will be from 9 to 1 p.m. It's like, think of it as a brunch. But like that, in addition to that core, there'll be plus in the core there is hot tea, actually black tea. I'm having it, if you can see it here right now. So Turks per capita, as far as I know, drink the most black tea in the world. So day in and day out. So that's the core, and then there'll be lots of sort of egg side dishes and some meat-related side dishes, and tons of different cheese and whatnot. So it's but the culture of it is that it's certainly on the weekends people like taking their time having breakfast.
All right, I'm hungry already, and yes, I want to do this. There's a place here in Lisbon that does it, so I need to somehow make a trip. The last time I was at a conference, I went to the Turkish booth and I said, "Hey, what conferences?" So if there's a conference organizer watching this, I want to come to Istanbul. I talk to them, invite me. In fact, I'm going to send them this video. This is remind you to invite me to Istanbul.
Okay.
Turkish breakfast.
Yeah, perfect. Yeah, great. Yeah, I've never been to Portugal, but I'd love to. So I haven't been to Spain either. So that's a part. My wife lived in Spain, and she speaks very highly of it. But that's a part of Europe I haven't been to. So if there's a conference there, I'd like to go.
Please do. Please come. So let's talk a little bit about technology. You said that you went straight from your college, you spent your college years in the US and you went to Yale. You got your degree in computer science and economics. Why
That's
did
right.
you choose economics?
I don't have very great answers for the decisions I made back in those years when I was that young. So, uh, computer science was certainly because my brother was doing it in Turkey. And I didn't like, I wanted to do math, I think. And I was kind of a bit discouraged in the family to just do math, like just pen and paper work. And I hadn't code, I hadn't much interest in coding. And I'm not really a good programmer, frankly. Uh, but it was clear I'd want to do something in a very quantitative discipline. So that's the justification for computer science. And for economics, it was extremely popular at Yale. Extremely popular. You know, everybody, like my roommates, my closest friends, they were all doing economics. So it was kind of in the culture of the campus that you take a 2, 3, 4 economics courses. So I did that, and I can't say I truly enjoyed it, frankly. Like it didn't resonate with me much. I didn't like the theories we were learning, but it was also easy to get degrees in a liberal arts education. So liberal arts educations like Yale's, the course requirements are relatively small. So a lot of people do double majors. So I kind of completed it, and I did end up taking a few very courses though. Like I took a game theory course, which resonated with me a lot, and I kind of like that theory a lot. So, and but the way I kind of began taking courses in economics was everybody was taking it, so I wanted to explore. And then after 4 or 5, I was like, okay, I might as well finish the major. That's what had happened. But I never really went into economics. I did go to computer science basically afterwards.
Now, you just said that you're not a very good coder.
I am
So
not.
that
Yeah.
surprised me. Okay, so what are you good at?
I think by my nature, I always incline towards kind of pen and paper work, like designing things and thinking hard on pen and paper. And so that's part of the reason probably also my PhD thesis was highly theoretical. And then I did realize though that I need to at least do more. I mean, we can talk about this later. I needed to do more applied things and focus more on applied things in the field, because I think you can do more impactful things if you actually produce software artifacts. So I was convinced of that. But after college, I have a little bit of career as software engineer at Google. So before my PhD, I did go to Google, and I could see I wasn't very good at it. Like the people had much deeper interest in coding and producing software and learning new technology, and I had the inclination to just go deep, do one thing, like focus on one thing, but try to understand it very deep. So that opportunities arises, I think, if you are working, say, at a company like Google, if you worked at their database teams, so those infrastructure software, I could see that many of those people were very deep into their field, that those are harder technologies compared to the type of work I was doing, which was like build a Java application, build a JavaScript front end and things like that. And I wasn't very good at it, and I wasn't also very interested in it. And I had trouble switching to those technologies that I had more interest in, that I thought were more sophisticated, that required maybe more education as well, to database teams, because they really required higher degrees. So that kind of was a signal to me that maybe I should go get a higher degree and learn some technology very well, and then I could decide if I want to come back to Google or a company or continue. So yeah, but I think I can say I'm an okay programmer, not a very good one. Yeah.
Okay. The other part that was surprising was that you went to Yale. Not that you aren't smart enough, but I think you are the first person that I've met other people from Yale, but you're the first person I met with a computer science degree from Yale. But what
Yeah.
brought that about?
Yeah, that's actually probably true, because when I was going there, now I'm sure it's very different. When I was going there, we were 8 people out of, I think, 1,400 students of my batch, my year. I think only 8 graduated computer science, and maybe like 10 or so with some double degrees. There was a couple interesting double degrees, like computer science and philosophy and things like that. Yeah, but certainly a handful of us were graduating back then. It was not a very popular thing compared to something like economics, where hundreds of students were majoring it, or something like history. So I'm not surprised actually that you haven't met people with a computer science degree from Yale, because it was an extremely small department. The last I checked, I think they were certainly closer to 100, and it was a much more popular degree right now there. Sorry, but what was your question? So I just
You answered my question.
Yeah. Okay.
But now I'm even more curious about, okay, you go straight from Turkey to an Ivy League school. What even brought that about as well?
So in Istanbul. So I'm not from Istanbul, but from a nearby city, from a much smaller city east of Istanbul. I went to this school, but a lot of students who were good in academics in primary school or so, they would go to boarding schools in Istanbul. So I was one of those. I went to one of these schools in Istanbul, which there's actually two or three of these, where half of the school basically goes to United States usually, and a few to Europe to go to college, and the other half stays in Turkey. There's only a handful of such schools, private schools in Turkey. So I mean, it's kind of like by luck that I ended up at that school, but I did somehow. And then at the end of high school, they would advise students to apply to American universities primarily. And I mean, I ended up getting acceptance from Yale. So that's how I ended up at Yale. Again, not many. It was not a very popular route. I think probably more people do it because the country also kept opening up. But back then, we were one of the few schools. Like the school that I went to in high school was one of the few schools in Istanbul that did this. And it's really by luck, actually. My parents didn't know this about the school when they sent me. Like when I went there when I was 11, they learned about the opportunity to go to America when I was 15 or 16. They had no idea. So they just thought they were sending me to a good school. And I was too young to make these decisions anyways at age 11. But, so that's kind of part of luck, I think, that I have no control of. But it ended up, I think, being good. So, yeah. I'm very happy, obviously. This is a great opportunity to go to Yale. Just to give an example, I mean, I mean, some of these institutions in America, universities, are so prestigious and so strong, I should say, that you end up kind of learning material from real kind of inventors of things. So I learned, for example, databases from Avi Silberschatz. Avi, and I have very fond memories of taking his lectures. Avi was teaching out of his textbook, and I'm still using the same textbook at University of Waterloo right now. So like, it was clear when I was taking the material from him, he was super excited about databases. He'd tell tons of stories about sort of the development of databases and history of databases that he witnessed. So he saw the field emerge from like 70s till when he was teaching early 2000s. So it was amazing. Like, you could meet these people who kind of influenced you a lot in terms of your intellectual curiosity, I think. So it ended up being good for me. I think it was kind of me starting to take databases with Avi, kind of put that into my set of interests. And I ended up doing a PhD in the topic, and now I'm teaching it and have a startup company and whatnot. So it did have a big effect.
That's why I do this show. When I pitched you this show, I said I really want to show the people that when we go deep into technologies, it's not just all of a sudden Semih decides one day I'm going to go create a database. It's this very big thread throughout your life. And
that is right. I mean, I can tell you how like luck is the biggest part of anything that I've done. When my students ask me like, how did you end up in databases? I say that I had interest in it through, I think, taking a course by Avi, and Avi, wrote one of my letters many years later when I applied to PhD. I didn't immediately apply. I went to Google for a while. But even when I was applying, I was a lot more confused. I wanted to do more theoretical stuff. As I said, by my nature, I am more of a pen and pencil, pen and paper sort of person. Like I like doing that type of work. And so I told Avi, I want to apply. I want to get a letter, but I also I don't think I want to do databases. I want to try to do algorithms. So he was like, no, you got to apply as databases, because in undergrad I hadn't done much sort of theoretical work, algorithmic work. So anyway, so I did end up going applying as a database person. Broadly systems, but primarily databases. I did talk about databases and networking, I think, in my application. Anyways, I got into Stanford for my PhD, and I did not align with the database faculty until towards the end of my second year. I actually first worked on algorithms. I actually did something really bizarre. I was doing DNA computing theory. So there was I had trouble finding an algorithms faculty, but there was one who was working on a very bizarre topic who was having trouble finding a student who wanted to prove things and do theory. And he was working on...
in a second when we go through that part of your career, and I think that would be interesting. Okay,
yeah. All right.
So from Yale, you continuing your string of luck, you fail upwards, or maybe fail upwards isn't the right word, but you continued your series of luck. I need to know how you get this luck. You go to Google, and would you do that again? Would you go straight from university to Google?
I think I would, for various reasons. I mean, one is that Google, this was 2006. Google was still quite small. It was still a larger enterprise, but much smaller than what it is now. And that's where I really learned programming, because I think it was a good skill for me for later parts of my career. So those 3 years that I worked at Google, I coded, and the mentors that I had there really taught me how to program. It wasn't something I really learned very well. And it's not something you can really learn well at school only. If you're somebody who kind of programs for fun, and I'm not a person like that, as I told you, I had not coded a single line of code until I came to university. You can't really pick it up just with coursework. So those 3 years were the years where I coded a lot and understood how to sort of write good programs, which ended up setting me up to do applied work later on in my career. So that was good. The other part was that, I mean, I was very young. I was making money for the first time, and I was in New York. So I went to the New York office. So those were probably the most fun years of my life, those 3 years, where first of all, I think working at Google wasn't hard in terms of the schedule, sort of how busy you were. So Google was quite a relaxed place. So I could travel a lot. I found a lot of time to do other things. And all my friends were in New York, and New York is just a very fun place. So I certainly want to have that experience again. So that's a part of my life that I look back, and I have very fond memories of those years at Google.
So you said that you were mentored by somebody. What did they mentor you, or what did they tell you that influenced you and how you wrote better code?
That's hard to answer. I don't know how to answer that, but there were very strict code reviews back then. I don't know how it is now, but then I would kind of write a program. So I was writing, for example, database applications, not the database layer. I wasn't writing the database, but I was writing applications that uses some internal databases for some Google applications. And, there were very strict reviews that you'd iterate 5 times, 6 times with these medium level, now very senior engineers, but like medium level engineers who were much better than me. And I kind of learned, I think, sort of a lot about the principles of programming, getting right object-oriented abstractions and testing rigorously and things like that. So that is how much I remember. It's been 20 years, by the way. But I know that's really the time of my life where I did routine programming all the time as a job. But I do remember the code reviews and how strict some of my mentors were in the teams that I was at, reviewing those code. Yeah.
So what I was wondering is you're saying you're not being a very good coder. So you're either being humble, or you fell through the cracks of Google, where I keep thinking, how come you get fired? How come you were good enough at Google to stay there for 3 years?
I don't think anybody was getting fired. I mean, I was good enough, I should say, but I also could see that I wasn't going to be like some of these people that were sort of in the teams that I wanted to be in, like the senior engineers of people who were developing databases, internal infrastructure tool. And Google had amazing set of infrastructure software. Like they had something called Chubby, they had a Borg, they had Bigtable, these databases. And the teams who were developing those, I really looked up to them. But I could also see there's no way I could probably rise up to that just through Google and trying to find my way through Google engineering stack. I just needed to learn a lot more about some of these technologies. And even in the applications that I was developing, like medium level, senior level engineers, they just had more interest and more passion for what they were doing than I was. So that's kind of the point that I was saying, like, when I was given task or when I kind of took task, I was good at it. I was fine at it. So no, I don't think I'd ever get fired from Google. I also never saw anyone get fired at Google, by the way, in those years at least. But I could also see that I'm not going to shine there. Like I'm not going to be, like I didn't have the drive or passion to say, you know what, I can focus and become like a great engineer who starts up teams at Google and whatnot. Like I just didn't see it in me to do that. I just didn't have the interest, I think, except if I went to, again, these infrastructure software. And there was another problem. It was just like, I just didn't have the background to do any of that work. So nobody would take me. I actually did apply a couple of times to go to some database teams in New York. There was actually one, I think. And they're like, no, like we're really looking for people who did at least database masters and mostly database PhDs. So that was clear to me that if I wanted to work on those tools that was really fascinating me, I had to find another route. It wasn't going to happen with me just staying at Google.
Well, that leads us very nicely into going to Stanford for your PhD.
Yeah.
So you really, it sounds like you saw that the only way that you could get to the level you wanted was to do that PhD. So now I paused you on a story about your PhD. You did your PhD in databases. And so somebody was around looking for a student to do what again?
So when I applied, so that was kind of my backup plan to do something in systems, so something in databases. So that's how I applied. And I do remember talking to, again, a couple of my faculty at university, Avi for sure, and I would sort of tell them, I have this, I did well in your course and you saw that I'm interested in systems and whatnot. And he would write me a letter. But I said, I actually want to explore a bit. Like I might want to do algorithms. I might want to do something in algorithms, just because I also know that that's in my, I've been this pen and paper person, as I said, by my nature. And, they advised me to not apply as a algorithms person to a PhD, but apply as databases or systems generally. And then just see once you're in, if you can find an opportunity. So I did spend a few years in my PhD just trying to look for an algorithms advisor, like an advisor in algorithms who does theoretical work. I did find one, but it was in a very bizarre topic. It was in a topic called DNA computing. It's a very cool thing, a very niche research area where people are trying to program DNA sort of strands to do computation within the cell. And then they're building a theory about how that could be done. So you're like taking the nucleotides A, C, G, and T, and you know what binds to what. And then you throw in a bunch of sort of DNAs together, they hit and sort of kind of get into interactions with each other, and then they end up performing some computations. It's a very, very niche, very bizarre topic. Anyways, so I did that for a while, but after a while, I just said, there's not much future in this. So then I went back to my comfortable zone of databases, got aligned with the database faculty, and ended up writing a PhD thesis in databases. Yeah.
All right. Tell me more about that PhD.
So I had two parts to my PhD thesis. It was really an umbrella kind of topic. There was one line of work I did with my own advisor, like official advisor, Jennifer Widom. Jennifer Widom, usually her style of research was that she'd start a large project and like a systems project, and then she'd have a few PhD theses on that same system for a while. So she did work a lot on XML databases. She worked on triggers. She's primarily, one of the things that she's most known for is her work on triggers the trigger feature in databases. She did a lot of work in that and in standardizing those as well, and stream databases. She did do a lot of good work on stream SQL standard, for example. Anyways, by the time I had joined her, though, she didn't have a good big team. She was kind of winding down her team, and she was getting more into administrative work. So she was the chair of the department. Then later on, she became the dean. She's still the dean at Stanford. So I did a solo project, basically, solo systems project, though, where it was a time where people were building a lot of MapReduce-like systems, so distributed data processing systems. And like Spark is probably one of the best PhD theses that came out of that era from Berkeley. And I was in the graph space. So there is a paper by Google called Pregel, which was essentially MapReduce for graphs. So and there was no open source version of it. So as the first thing I did was I built an open source version of it. That took me a while to build something that could be usable. And that became the foundation on which I did several work, kind of optimizing those systems, figuring out sort of how do you write algorithms that work well on those systems. So I did write several papers in that part. So that Pregel-like systems is a big part of my thesis. But as I said, I was always interested in theory, pen and paper work. So I also had a second line of work, which was actually more extensive, with Jeff Allman. Jeff Allman is a theoretician. He does a lot of sort of theoretical work in databases, but also, I think a lot of people would know Jeff through his work in compilers and algorithms. So he's extremely prolific. He's got, 7 to 10 textbooks in different subjects in computer science. He several years ago won the Turing Award for his contributions to not databases, but compilers and programming languages, actually. So Jeff was the person to do theoretical work in databases. So I worked with him on theory of MapReduce-like systems. What that means is that you've got algorithms running on these distributed systems, and you want to be able to say something about their optimality. You want to say, okay, so here's a parallel distributed algorithm, and this is how much communication it results in to perform some computation across the machines. Is that a good amount? So like algorithmic frameworks to understand if a particular join algorithm is good, or if a particular, sorting algorithm is good, and things like that. So I did a bunch of theoretical work in the theory of these distributed systems, and then I did build a distributed graph sort of data processing system. So together, in the end, we put that together and called it a thesis, which is what happens in the last phase of any PhD thesis. Usually is this effort to, okay, now how do we come up with a story that now that you've done all this work, put it together. So that's what ended up being my PhD thesis.
And when you do a defense on a PhD thesis like that, is the defense showing your code, or what sort of defense do you have to do?
The defenses are usually quite anticlimactic. It's usually 20-minute to 30-minute high-level presentation of the work that you did, because the committee has already read your thesis. At least that's how it is at Stanford. It changes from institution to institution. Sometimes the committee does not read the thesis before the defense and reads it afterwards. Sometimes, but I think often they read it before. And then you just have a kind of a traditional 20 minutes, at most half an hour presentation summarizing the work that you did. And then it's an hour and a half, maybe a bit longer questioning, where they ask about different chapters of your thesis. A lot of it is symbolic, usually, like certainly like your advisor, for example, is in the committee, but doesn't ask many questions. And then there's a couple faculty members who can probe you on things. Like Jeff probed me a lot in my PhD thesis, like actually asked me to solve a sort of somewhat theoretical problem on the board in front of the committee. And when I tell the story, people say that's extremely unusual. But anyways, so some kind of questioning about some different chapters of your thesis is the rest of the defense.
Okay. And so you originally joined or started your PhD in order to perhaps even to go back to Google. That I think that's what you said you were originally wanting to do. But what you ended up doing was going to the University of Waterloo. Why did you join a university instead of going back to, let's say, a Google or some other database company?
I think towards the end of towards the end of my PhD, I realized PhD is something that gets better as you become more senior. I didn't really enjoy the first years of my PhD, but towards the end, it started becoming fun because now you could see that you can come up with your own problems. You can get creative, start sort of these research projects from scratch. And I just realized I'm just going to be happy at the university, I think. There isn't a much deeper reason why I didn't consider going back to industry. I guess I could have, but I thought I was enjoying research good enough that I wanted to see myself as a faculty member somewhere. So I did academic job, applications only, and yeah, luckily, I didn't have actually any interviews from North America except Waterloo, and luckily that turned into a job offer. I did one from Turkey, but it was kind of like a backup thing in case I wanted to go back home. So I kind of ended up. I had a very, it was always a hard part of my life because I wasn't getting any interviews. But then I did get one, so it was also the minimum amount of work that I ended up doing because there was only one interview and that got converted to a job offer. So I'm very happy about that. And it was a place I liked because that there's a good database group here, and Waterloo has a good reputation. So I've been around since then. I've been here for 9 years.
Yeah. The string of luck continues going to the University of Waterloo. If people don't know, some of my friends who they went to University of Waterloo too.
Really, very nice.
Yeah, and got amazing. They're in the database community too. So yes, luck. I need to figure out. We're going to have to do like an hour-long interview just about luck. What do you do that's so lucky? Where's your rabbit's foot? You're American. What's the equivalent of a rabbit's foot in Turkey?
I don't know. I'm not sure, but I actually don't know what's a rabbit's foot.
A rabbit's foot is when you would hold it for luck. So there's something that's an item that's inherently lucky. So just by having a rabbit's foot, you would be lucky.
I actually don't know. I don't think we have that. I don't think we have that in the Turkish culture. I might be wrong, but I can't think of something.
Or another American one, it was more in the West. You'd have a horseshoe above a door, and that would bring you luck.
I see. I'm not sure if we have it for luck. We have it for we have these evil, like the blue eyes, the blue things. That's the evil eyes. So we have that to protect against protect against bad things happening, stuff like that. I'm not sure if we have it for luck. I don't know if we have it for luck.
Okay, well, you're gonna have to report back to me. What is so lucky? What is this lucky thing? It's the breakfast, I think.
Yeah. But it's also it depends. I obviously I do find myself extremely lucky if you keep a large perspective. But there were periods of my life where I felt really unlucky. So, for example, when I was in PhD and I was working on my open source version of Pregel, so Pregel was closed source, right? Like really a couple of weeks before I was going to put out my work in the open source, Facebook announced an Apache project that's also a clone of Pregel. And that's, that was very unlucky. I didn't know it was happening in parallel, but that kind of took a lot of steam from my PhD thesis. So there was like periods of time where I felt like, okay, maybe this line of work is not going to go anywhere. But continue doing work, and as long as you keep accumulating, you do produce something. But I did start producing very late in my PhD compared to my peers. So those were years where I was feeling like things aren't going the way I want. I published my first paper really in my fourth year, which is quite late for a lot of PhD students. They end up publishing in their second years, third years for sure. I didn't until my fourth year, but then I was able to publish enough to put together an application. Yeah, I don't know. Everybody probably gets. Yeah, I mean, I do feel. Yeah, I do feel quite lucky, frankly. Yeah.
So your background in private industry, how do you think that helps you as you teach?
Right now, I wouldn't say it's my experiences at Google that helps me teach much, but the fact that I am doing more applied work and I have a company, and from the company, I can follow industry better. That helps, I think, for me to pick better problems. I'm not sure how it helps me to teach. Like when I teach, we're teaching about very foundational things. Like, if I'm teaching a course in Introduction to Databases, you end up sort of teaching relational algebra, relational data models, SQL, theory of normalization and things like that. Those are quite formal things. I do squeeze in a lot of stories about sort of database history to my lectures, just because I think I'm trying to connect people to the real world sort of implications of the formal foundational things we are discussing in lectures. Like, why was the relational model sort of so successful? I tell stories about the debate in the beginning of the birth of data management, where there were two classes of data models. It was called the network model was one school of thought, and relational model was another school of thought. And then, there was kind of a decade or 2 decades of kind of competition between them, and then the relational model wins. And I tell about the industry stories of like, okay, IBM built this, and then Oracle built this, and then Microsoft built this, so on and so forth, so that people, I think, see that this is a very applied field. Like databases is a very applied field. There's a big industry out there. It's also a good career opportunity for people who want to go in this direction. So I do squeeze in a lot of stories like that. But I think the fact that I'm closer to application sort of practitioners now because of Kuzu Inc. and the startup journey, which we can talk later about, helps. Doesn't maybe not the teaching, but helps the research a bit more. I'm a lot more practical oriented right now than I was. Certainly during my PhD years, I had not a lot of concern for practicality. Now I do. I think, yeah, every problem that I want to pick, I want to know that it matters for the systems. Otherwise, I'm going to be very discouraged right now.
Speaking of teaching, what's your favorite concept to teach?
Yeah, I wish I had a very good answer to this. This was, I think, I taught basically 2 main courses. I mean, I taught several different seminars, like grad seminars on database technology. But in my undergraduate teaching, I did teach, I taught database introduction to database and introduction to algorithms. And I find introduction to algorithms, those concepts to be a lot more popular. They resonate a lot more with students. And one thing that I've gotten a lot of good feedback on is whenever I'm the first person that ends up teaching dynamic programming to students, I get a lot of feedback because they get that a lot in their interviews. So I get a lot of sort of positive feedback saying, thanks, professor, this dynamic programming appeared in this interview with this company and I kind of nailed it. And so that is one thing that I think that I can highlight as when I teach about sort of algorithmic design principles, dynamic programming, divide and conquer, and so on and so forth. I do get a lot of good feedback about those, and especially about dynamic programming. Yeah.
You reminded me of something that I'll tell everybody, and that is when we teach. So I've taught a lot too. I wasn't a professor, but I taught a lot in data engineering. And what was the most validating part of teaching is to have somebody reach out to you. Maybe it's not immediately after, maybe it's a few years after, and tell that person who taught you how that affected you. How did that help you? How did that, because that's why I did it. I put all these seeds out into the world, and the seeds of my knowledge, and I'm hoping that all those people are able to do great things. So reach back out, tell them.
Yeah.
I've even done it with some of my high school teachers. I talked to my high school Spanish teacher and said, "Hey, guess what? That kid who grew up in Montana, he speaks fluent Spanish and now lives in Portugal, and I have passable Portuguese, and I've
Yeah.
traveled all around these Spanish-speaking countries, and I go and speak Spanish fluently there." You know,
Yeah.
those sorts of things. That's validating to them.
Yeah. So I have a story I can tell here where when we were in middle school, we had a science teacher, actually, not even a math teacher, who was teaching us probability a little bit, just trying to give us an intuition. And I do remember, I think this is like pedagogically, I understood the importance of teaching with an example, the importance of this through this. This is like a story that has always stayed with me, where she was trying to teach us that, you know, it's actually a very hard concept to teach to middle school students, and I don't think we understood it, but it still fascinated me. She was trying to teach us that, you know, if you, for example, flip a coin, you're going to get 50% heads and 50% tails, right? And if you wanted to convince yourself that this is going to happen at 50-50, you know, you could repeat this a lot. And if you repeat this like many, many times, you will see that it's actually really close to 50-50. So she gave each one of us a card, and where one side was black and one side was white, and she asked all of us to cut it into 100 pieces. So we did that, 100 pieces, and gave us a bag, and we sort of shook it, and I said, now do the experiment, sort of put all of them to the, you know, pour all of them to the table and count how many are white and how many are black. And I do, and she said, you're not going to get something like 40 and 60, I guarantee it to you. You're going to get something a lot more closer to 50-50. And I did get 49-51, I think. And I was so fascinated how she predicted this. Like, because to me, it sounds like it could really come up 100 whites and 0 blacks. And I was like, okay, now why that? Like, it just rose my curiosity to a level where I was like, okay, why did that happen? And I do remember kind of experimenting with it to see if I could really get 40-60, and I couldn't. It's actually very difficult to get 40 and 60. So later on, I learned the principles of this much later on, obviously, when you learn about probability distributions and densities and whatnot. But it's still like, for many years, I kind of remembered this phenomena, like, why can't I get 40 and 60? Let me repeat the experiment again. No, you're not able to get that. So but it's, you know, you know, now she's not going to be listening to this, but you know, that's a story that where, you know, if I could find her, I would say, like, you know, you did a very good job. Like, you did raise my curiosity, and now, you know, I learn and I teach myself, and I do try to come with the principle about, you know, can I give an example that will make this very clear to them, or raise their curiosity. So it's I think it's a good aspect of teaching, a very fulfilling aspect of teaching is stories like this.
So now we're going to move on to the whiteboarding show part of the show and talk about what is Kuzu.
What is Kuzu? Kuzu is an state of the art, I would say, embedded graph database management systems. It means we implement Cypher, Neo4j's language, and implement the property graph data model, a version of it. It's a lot of the usability features of Kuzu is kind of modeled after DuckDB, so it's embedded. We can scan sort of external sources easily in Cypher. And
Would you mind drawing that out for us so that we can visualize it?
What's a good way to draw? So basically, the main usability feature is that if this is your app, the database essentially Kuzu, I'll put it KZ. Is this is very small, I guess, right, on your screen? Yeah, I'll draw it a bit. I'll draw it a bit larger, maybe.
Yeah, that's fine.
Okay. So so if this is your app, embedded databases run as part of your application. So meaning that you don't set up a server. It's like SQLite. You don't set up an external server to connect to it. Where they start and die with the application. When you start your application, the database starts. It's a library that you import in your application, and when you're closed down, the database closes down. It doesn't mean it's temporary necessarily. They can still persist the data on disk, but the software part of the database is part of the application.
So that ephemerality here that you were mentioning. So what you could do is you could persist this out to some sort of S3 or local file system, and
That's
then
right.
when we relaunch the app again, pull that in again.
Yeah. So maybe a better way to actually draw this is the default mode of embedded databases. Is that this is the DB software. That's the software that's running, and then there's an external disk that it's writing to. So it will this is your external disk or maybe S3, whatever, but something that you can use to persist. But the software, there's no server basically. It's a library. So your queries will get compiled and executed within your application. We're using the threads that are running the application in some sense. They'll run their own threads, but the main interest in the database will be the thread that's running the application.
So since you're talking about threads, is Kuzu single threaded, multi-threaded?
It's multi-threaded. We use by default, it's configurable, but we use by default every core in the system. And we also use by default 80% of the memory in the system. But these are configurable when you start your database. So basically you do something like, DB in Python, let's say, you do something like, you'll say something like import Kuzu. Oh, I can't write for some reason very well. I wonder if it's my end. Yes, KZ. So you do import db is equal to kuzu.database. You open an object, and here you can put some configurations that tell how many cores we want to use, how much RAM we want to use. But if you leave them empty, you also point it to a particular file. If you're opening it as a persistent database, meaning that you want us to write the data to disk. But you can also give other configurations, and depending on that, we'll use some amount of cores and some amount of RAM in your application. So it's important to know this because we share, like the Kuzu that's running as part of the application will share the RAM of the application in the applications, the process that the application is running in.
So as we talk about that RAM usage, so here we have Kuzu, let's say you said it was using by default 80%. Let's say we had something that exceeded our core memory. Does Kuzu have the ability to put that to disk and rehydrate as is necessary?
In some operations, not in every operation. So we are not as competent as a system like DuckDB, let's say. So DuckDB and maybe SQLite, I actually don't know what SQLite's capabilities are there. They can, for example, if you're running a query and in the middle of the query you realize you're running out of disk, they might have abilities to spill things off. We do that for some queries. So, for example, if you've got on your disk, if you have a large file, some Parquet file of say person nodes, person records. I can't write, sorry. And another one, and these are very large files, maybe 1 terabyte, and you got only like 128 gigabytes of RAM or something. When you say in Kuzu, copy this data into this node records, node table. So we have a notion of a node table and a rel table, relationship tables. In the property graph model, there are two essentially concepts, nodes and relationships between nodes. These are labeled. So if you say, for example, these Parquet files, person Parquet files, which is very large, they need to be, I want to put them into my node table, person nodes. So they're going to be person nodes, but it's very large. And it's 1 terabyte and you have less terabyte. There we do a lot of optimizations to make sure you don't run out of memory for that query we do. But if you're, I don't know, finding some kind of pattern across your graph, and then we run out of memory. Right now, we will run out of memory. We don't have a way to spill, but it's like there's an open issue about this that we want. This is something we wanna handle as well.
Okay. Yeah, that's as you get into this embedded model. That's something you have to think about a little bit more. So good that you're thinking through that. So interesting. So you briefly touched on this Parquet file. Is Parquet your method of choice for storing these files?
So this is we have our own internal file sort of format to store the database. Most of the data is stored in a file called, so when you open a database to a particular directory, let's say database directory DB, right? We'll store several files under this. The main database file is something called data.kz. That is you can think of it as a columnar format like Parquet, but it's more advanced because it also stores indices based on the relationships that you have in the database. But in my example, what I was showing here, this is just any other Parquet file you might have on your system, which you want to convert into Kuzu's format. So which basically you want to load into your database. This could be Parquet, it could be CSV files, it could be JSON. We have ways of natively ingesting data from several different file formats. We also have ways of ingesting data directly from some other relational databases. So you can open a connection to you can kind of open a connection to DuckDB or SQLite or MySQL. I'm not sure about MySQL, by the way, I should check, but several of these, and sort of directly move certain tables, contents in those databases to Kuzu, and they will all ultimately, this is our format, data.kz is where we store the Kuzu database.
Okay, so when we talked, we first met at Connected Data London, and when I talked, and a lot of what was the secret sauce of Kuzu is in these files and how you're laying out the files. So let's go to whiteboard 2, and would you mind drawing out this file format and why it's so important?
Yeah. So I think maybe I should start with explaining two things. So there are two components of the database, or two different sets of records. One are node records, and we call them node tables, and the other are relationship tables. So now property graph model is a graph-based model. So you're looking at something like this. Maybe this is a person node, and this person follows this other person, and this person maybe likes another person and has an account in another node. So some of these records are modeled as nodes, and some of these are modeled as edges. So like a follows edge, a likes edge, a has edge, so on and so forth, has account edge, so on and so forth. So they get modeled essentially as separate things. They're all tables. We look at them, all of these as tables, but like the person nodes would be person node tables, and the follows edges would be follows rel tables. And there's some kind of constraints about, like, for example, rel tables need to be referring to a from node table and a to node table. So they are directed edges. So in our own format, these get stored a little differently. The nodes are easier to explain because it's very familiar to people, similar to how to columnar formats that analytics relational systems store their tables. So if you have a person records with person nodes with ID and name, for example, properties. So these are your records, and you said this is a node table, and its label is person. So what we do is we chunk this into what we call node groups. So it's like the row groups of Parquet. And it's columnar. So the first thing is that it's columnar. And then it's going to be chunked into what we call node groups. which is just like row groups. It's going to be very familiar. So this data, these IDs, they will be put together, stored separately in a separate part of data.kz file, and the names will be stored in a different part of the data.kz file. Moreover, they will be chunked into pieces, into these node groups, meaning that the first 100K or so of these, so maybe let me pick another color. So the first 100K would be node group 1. And that means, and this would be node group 2. What that means is that we'll take these IDs. Oh, sorry. I don't know how to do this, but we'll take these IDs and then we will store them, like 100K of these IDs, compress them together and store it somewhere. And we'll take these 100K together, meaning consecutively on the data.kz file. We'll take these 100K IDs, compress it, apply some compression algorithm and store it, so on and so forth. Similarly, we'll take these names, strings, consecutively, compress it and store it consecutively, and these names consecutively, so on and so forth. So it's very similar to how Parquet stores its own records. Is that fine?
Yes.
Yeah, okay. So then the relationship tables are more interesting. The relationship tables, if you have a relationship table, so you'll have a from, it needs to have a from and a to, those records. And you might have some properties. So let's look at something like follows. And maybe it's got a since property, which, since when is this person following this other person? So what we will do is, this is more advanced. So you got stuff like this, this is person 1. These are internal IDs, let's say. Normally in your CSV files or Parquet files, they're not internal IDs. So they are kind of foreign keys to the node tables that are being referenced. So from is a person here and to is also a person. So in your raw files, you will write something like Alice and Bob, etc. But when we store it, we don't store those, duplicate those. We just know the internal IDs, internal offsets, if you will, of those person nodes. So you could have a from 1 to 3, 1 to 17, 5 to 4 with some dates here. And again, maybe 1 to 24, so on and so forth. So you have these records. The way these will be stored is what we call in CSR, compressed sparse row format on disk. Is this normal that I'm having trouble writing?
No, it seems like you're having more trouble. I'm not sure why. Yeah.
I don't know. Let me just. Yeah, no, I have enough. But anyways, let me do my best. So the CSR format is something like this. You have in abstract 2 parts of a CSR, and we'll do essentially 2 CSR data structures on disk. This is a compressed way of storing. Let's just focus on the from and tos. Let's forget about how the since are stored, just the from and tos. What we'll do is we'll basically suppose this node 1, person node 1, has 3 forward edges, and they are 3, 17, and 24. So over here, we're going to put this 0, 3, and maybe person with node 2 has 4 edges, so we'll put 7, and then maybe person with node 3 has also 5 edges, so or like let's say they've got only one edge, so it's maybe 8, so on and so forth. So what this means is these are called offsets, and these are the actual neighbor IDs, the actual values basically, neighbor IDs. This means that the first 3 values here, so 0 to 3 means if I'm interested in the first person's edges to locate them, I need to find essentially it starts at 0 and it ends at 3. So anything that's in between offsets 0, 1, and 2 basically are person 1's edges. So I will put 3, 17, and 24 in my example. This is 17, 24 here, right? So that essentially identifies this part, identifies person 1's P1's edges. And then 3 to 7, suppose it's something like this part. So that becomes person 2's edges, so on and so forth. And then the next one, 7 to 8, becomes person 3's edges, so on and so forth. So that's the rough format. This is not sorted necessarily. These are not necessarily sorted, although I wrote them in sorted order. We don't necessarily sort these. But basically, you can think of this as that we sort by the from column. So we get 1, 1, 1, 1, then 2, 2, 2, 2. And then we compress the 1, 1, 1s and then 2, 2, 2s. But it's similar to run length encoding, but it's a different representation of this. So this is the essence of a CSR format. We have a disk-based version of this. There's a couple sort of differences from this is the textbook CSR people would put into computer science textbooks on data structures. What we do is, for example, we leave gaps after each sort of list. Let's call these adjacency lists. We leave gaps so that if there is more edges that person 1 gets, we can append it without kind of sort of sliding a lot of things here. So that's the first thing. The other thing is that this is actually also sort of, this structure is also chunked into node groups. So basically for say 100K nodes, like maybe this part, 1 second. So for 100K nodes, and their edges, so maybe until here, they get stored as 1 unit somewhere on disk, and then the second 100K nodes edges to be partitioned and stored separately, so on and so forth. So it's kind of an extension of this node group idea to the CSR list. So that's how everything kind of gets laid out roughly in terms of rels and also nodes.
And also good reasons why you don't want to write your own database. So here, let me repeat some of this stuff back to you. So here you gave this example of, here we have person 0. Since person 0 doesn't have anything in there, they would have a node count of 0. So
actually, sorry, I let's call that a typo, because I meant that this is, so normally the right thing would be, so okay, if there's a person 0, 2, let me fix this. It's a good point. I would have another part here, which would, so let me first erase this. So I would have another part here with 0. So, okay, so now this is more accurate. So this basically means that person 0 starts at 0, but also ends at 0. Okay, so which means it has no edges. Person 1 starts at 0 and ends at 3, so it's got 3 edges. Person 2 starts at 3, ends at 7, so it's got 4 edges, so on and so forth.
So when you do your calculation for read offsets, you're basically looking at this and saying, okay, I'll need to go n number within this other file to find where that is.
Exactly. Yeah, that's how it happens. So this is kind of an offset, compressed way of quickly finding which part of this other data structure that the edges of a particular node are. So suppose Alice is person one, and we're interested in the people that Alice follows. So the scan operator will basically figure out, okay, which part of the CSR do I need to read first by inspecting this, and then calculating this, and then obviously this is mapped to some disk pages. Then we kind of further map it to, okay, which part of the disk pages and bytes exactly that we need to read. So that's the calculation that's done.
Okay.
But again, so I guess like one thing I should say is that all of these, both this part of this is a little high level structure, and this part of the high level structure is chunked into pieces, and each chunk is compressed independently. So we do like bit compression and things like that on these structures.
Okay. So if people, just in case people are having trouble following this part, so this is the on disk format, which then would be translated in more of a row format, columnar format, table format, as it were, into something like this and this, that if you were to represent it in more of a graph notation like you're used to of a DAG, that's what these two things would eventually form into. So it's kind of the circuitous route that brings all that. Is that right?
You're going, yeah. This is kind of the on this is the on disk representation, right? This is kind of maybe logic, like this is a slightly higher level of like set of row representation of this, but users should look at their databases in Cypher like this. They have clear notions of nodes and clear notions of edges. So this is the most highest level, logical level that people model their records. Underneath, these are the bits and bytes that we store in this format.
One thing that you kind of surprised me with when we first talked was that you very strongly believe that tables or even graph tables should have a set schema. Is that your belief?
So yes, in the sense that it's a decision we made in Kuzu, particularly because if you don't have a schema of your records, if you let it be very flexible, like Neo4j does, for example. Neo4j allows you to put arbitrary key values on nodes, arbitrary key values on edges. So that's obviously convenient for users, but it becomes very difficult to write a fast database if you don't know the structure of your data. So a lot of like the general principle in data management is that database systems can be fast because they exploit structure. So they know, for example, okay, each one of my person records has an ID and a name, which means you can now adopt these more advanced things like columnar storages. If you don't know the structure of your records, you can't do this because this clearly requires you to know the structure, like this type of advanced storage. So like classic things like compression, etc., which are kind of, I can't imagine fast databases without all these optimizations. Can't be written if you don't know the structure. So when we were starting Kuzu, we said, all right, our goal was to write an engine that was fast, but maybe we were going to give up this convenience that you can't put arbitrary things. So we said upfront, you need to tell us the structures of your records.
And you are able to do alters, is that correct?
We are able to do what?
Alter table, add
Alter table, yes.
schema.
That's right. Yeah. You can add new columns, drop tables. All of those are doable. Like a good way, I think it's probably the right time for me to make this point is that I have always looked at graph databases not fundamentally, and I know this looks blasphemous to people in the graph world, but so this is my conviction that I've never looked at graph databases at the system level much different than relational systems. So I've always said that graph databases at their core are relational in the sense that the high-level query languages are also very similar to SQL. They've got a different syntax, like a graph pattern syntax, which is very elegant for certain things. But ultimately, things get compiled down to these operators that take in sets of records and output sets of records. So which means the leaf nodes of your query plans need to be scanned. So you're scanning sets of records. What that means is that you're scanning tables. It's no different than that. So, a decision that we made is that, like the graph databases are fundamentally not very different than relational databases. You got, just like relational databases, you got set tables of records, but you just need to tell us which ones are your entities or nodes and which ones are your relationships explicitly. And then internally we do several optimizations, like creating this index, for example. This is like this is an index, basically a join index in some sense, so that given a particular node, we can find the other nodes that it joins with through this follows edge. So that's, you can think of that as an index to speed up some joins, and we'll do that automatically for you. And the reason we can do that is that you have identified which one of your tables are relationships and which ones are nodes, and you've told that to the system.
Yeah. So the kind of coming back, why I asked that question is this node table here benefits from having a set schema from more of a systems perspective, but I go even one step higher than that. And fundamentally, I don't believe that although we can be schemaless, I don't believe we should be as data engineers or as data people, simply because you kick the can. You kick a pretty difficult problem of understanding your schema, knowing what's there down the road a bit to somebody. Maybe it's a web developer, maybe it's on the website, that eventually has to say, oh, well, what is this? I need to display this in some fashion. And so now the person who has the least context will have to figure out how to display this to a user. And I think that's a fundamental problem, even in analytics. So you kick the can of, now a data analyst has to figure out what is the difference between data blob 1 and data blob 2 is. It's not what you want to do.
I agree. We've also had asked throughout many years, we were doing research in graph databases, asked people if when they go to production, do they also have records that don't have a fixed schema? And almost all of them said no. Like when we're prototyping, it's easy and we don't set up the schema, it's convenient. But when the time comes when we're more serious and we say, okay, we're going to take this graph database application to production, we do fixed schema. We do have fixed schemas. So it's a good print. It's a good kind of rule of thumb, is to make sure there's your records have schema. I agree.
Yeah, I've heard that too. Where frankly surprised me, where people are saying it's so easy to develop early on, and so you just have to add columns and they get added automatically. And I think, well, if you're using some kind of ORM, the ORM will add those columns for you automatically too. I think it puts you into something. It puts you into a bad form of, oh, we just add things and we do that, but then when we go to production, we don't go back and say, okay, now we've solidified the schema, or worse yet, you do a version 2. And what happens in that version 2? You have the version 1 schema, the version 2 schema. I think it creates a lot more problems than people think.
Yeah, I agree.
All right, well, good. So we talked a little bit about what makes Kuzu so fast. So you kind of alluded to it. How does an actual query plan work in this?
Good. Is there another whiteboard I could go to? Like, can I add a one?
Yeah, let's go to 3.
Let's go to 3. So you when you ask a query, so let me give an example. So suppose you're asking for match well, my pen works much better now. Something simple. Follows, this is E, follows. Okay, just for a bit. Now it doesn't work again.
You spoke too soon.
Yeah, it spoke too soon. I was trying to erase this. There's some of these things. So a person follows another person B. That's a B. And you got maybe a where clause and a return clause. So those are the 3 core clauses of cipher, where I don't know, a dot name is Alice, return b dot age, b dot name or something. So if you look at this, I mean, hopefully a lot of people will just see the resemblance to SQL. You know, this where is the same as SQL's where. This match is more like the from, where you do your join. Like you describe how your records are being joined. So you got a set of records that will bind to A, you know, per table A, and you got a set of records they will bind to E, B, but they're person follows person. Like you're just a person follows person join basically, but in this more elegant syntax. And then you're returning, this is kind of like your select in SQL, a.name. So the way that we compile this into a query plan is just standard. We follow standard wisdom in databases. So this will be converted into a plan like scan person. So you're going to scan the person records. A. And then, well, actually, so there's, I'll tell you a little bit of the interesting things that we'll do. So there's going to be a scan, a double scan follows this, but this is really kind of like for each A, we're going to scan the follows edges of this because we got this join index. We can quickly do that. And then what we'll do is, so you know, we can go deeper into this, but basically, actually, there's a where. So here in the scan or with a filter operator, we'll actually run the filter name is equal to Alice. Will be run either as part of the scan or as a separate filter operator. You can think of it as filter separator, where you get a special operator that does that together. So we basically scan what ends up happening. So there's more to this. We can go into this, but you get a plan that looks like this. So it doesn't look much different than a plan you'd get in Postgres, let's say. So there's these operators, they take in sets of tuples, they output sets of tuples. So one thing that we do that is interesting is there's one technique that we use a lot, which is this sideway information passing, so SIP. So over here, so suppose name is like a very selective predicate. There isn't many people with name Alice. So maybe suppose there's only one person with name Alice. So what you expect here is that after you scan Alice, so maybe one tuple, right? So maybe with only the person with ID, and let's say they've got an ID and a name, right, in my example. And person with ID 7 and name Alice is the only tuple that the scan finds. So the scan follows, knows that it only needs to scan the follows edges of the person with node 7. Right, so there's a whole nodes record, so maybe there's millions of records, nodes relationships in the database, but you only need the ones that are essentially have ID 7. So this scan 7 can directly go into the CSR over here and find, okay, this is maybe, I don't know, in my example, I don't have enough, but person 7, it inspects its offsets and finds, okay, this is the part of the data.kz file that we have to scan. So all that is done. So that's an optimization that's done. But then what needs to be done is that once we know the people that Alice follows, the query requires us to return the names of those people. Right. So this is where we apply what this optimization called SIP. So suppose word 7 has essentially 3 edges. You know, person 100, or maybe 2 edges, person 100 and person 108. So two people that Alice follows. So for the rest of the query, what we need is to find the names of 100 and 108 only. And the way we do this is that we've got a hash join operator here. A hash join operator. So one side will be this follows edges. Okay, so one side will be this 700, 708, right? And then we'll build a hash table out of these. We'll build a hash table using the 100 and 108, because those are the names that we need. So the other side of the hash join will be scan person. It's just a scan. Let me erase this. It's just a scan of the person tables. But we don't want to scan all of the Bs. At this point, after the hash join, after the hash join, after we build the build side, right? The build key is 100 and 108. The build values are 7 and 7 in this case. After we build the build side of the hash table, we only know that the only successful join keys will be 100 and 108. So only those should be scanned here. So we pass this as this bit filter. We call this node mask. So we pass this node mask. This is the sideway information passing. So this operator passes to this operator that, it's all zeros, 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 zeros. But for the offsets 100 and 108, we have ones, and everywhere else is 0. So this indicates to the scan that I need to scan the names of the person records, but only of 100 person with offset 100 and for offset 108. So only scan those. So normally in a sort of in a columnar system, say DuckDB, what would happen is that this SIP wouldn't happen. So you'd have this hash join that needs to join the outputs of the A person and E follows with the person records, but DuckDB would scan every person record, right? So our goal was to kind of minimize the scans as much as possible. And the reason we kind of pick hash join is that, well, I mean, let me not get in there, but this is the type of processing that will happen, and maybe we could go. I could go depending on your questions.
So the question I had was on this. I can't remember what you called it.
Node mask.
Node mask. If you had 1 million nodes, you would have 1 million entries in there. It was mostly zeros.
Yeah, think of it as a million bits. So it's very yeah, mask. Yeah. And it's got only 2 bits in it, but we still need to scan through it to know which ones to scan. So the scan operator essentially kind of looks at the bits and figures out, okay, I only need to read these parts of the disk. So it only reads essentially, if these are on 2 separate pages, it only ends up scanning 2 pages. And we use this very aggressively. Like there's a lot of query plans. Whenever we can do sideway information passing to minimize scans, we do that in Kuzu. So that's like one technique that we use. Yeah.
So one of the as I was thinking about this, is Kuzu optimized for smaller, I guess, reads? Would Kuzu have a problem with a very large, let's say we don't have a where clause and we just want to go through and have this exhaustive regression all the way down?
Yeah, so it's by default it assumes it's essentially crunching a lot of data, right? So the use of hash joins actually is the one motivation was that it's a very sort of common wisdom join algorithm to use for building analytics oriented systems. And by analytics oriented systems, I mean those that crunch a lot of data, right? So read optimized systems, basically. Like Kuzu overall is a query optimized, read optimized system instead of one where you can do a lot of transactional updates. We support transactions, but we're not designed to be very fast at tons of transactional updates. So if you're building an analytics engine, like which I think a lot of graph databases should be used for, they're all generally used for analytics oriented applications, which means that these are applications that crunch a lot of data. So it is optimized to do that. But these optimizations like SIP we have in the system are kind of optimizing the system to also work well when you're reading small amounts of data. So a system like Neo4j, for example, that does not generally by default use hash joins, what they do is, you read a person table, a follows table, and then they've got this operator called extend. Okay, so it's like a linear plan. There's no hash joins. And what extend does is that it basically takes those 100 and 108, like takes the output from the follows and then reads those names offsets. But the problem, like we didn't want to do that. That's not a very good idea. It's a fine idea if for a query like this, where there's only like a single node and their edges and the names of those, the neighbor nodes. But if you got a lot of kind of records nodes that are coming in from the scan, if scan is producing a lot of tuples, then for each one of those, you need to essentially scan, go and randomly scan the names of their names. So you take the first node, first person node, you look at its edges, right? Maybe it's got 10 edges, and then you read their names. And those are not necessarily consecutive, so you're doing random reads. Then you take the second node, second person node, and then look at their follows edges, and maybe that's got 20 follows, people that they follow. So you do 20 random kind of reads on this name column or name properties. So that's not very good if the scan is producing a lot of things. It's leading to a lot of random IOs. Whereas hash join plans, which columnars like analytics oriented systems do, they don't use operators like this. They'll say, okay, you got all the follows relationships, and maybe there's a lot of them, and then they'll create a hash table, and then they'll scan the person table once sequentially though, and then they will probe into this hash table. So all the randomness will not happen when you're reading from disk. By design, when you have hash join plans, and every scan is sequential, right? So you don't have these like extend like operators that could lead to random disk IO scans, disk IO reads. So to protect against that, we chose hash joins, right? But the advantage of, again, Neo4j like plans is that if the scan person here, where a name is Alice, produces only one, like few tuples, then this is kind of very fast because you're only reading maybe a couple sort of neighbors' names, and that's fine. You don't need to create a hash table. You don't need to do this additional scan, things like that. So it had this advantage. So we were basically we have a paper on Kuzu in the CIDR conference in 2023. Where we talk about exactly this problem to justify our kind of join compilation design or join part of the query processor that performs joins, to justify why we do hash joins and why we do SIPs. So this SIP is a way so that we can minimize these scans, but scans are still by default sequential. So we'll never do essentially very highly random scans that deteriorate if you're in a case like this, but the scan person A produces a lot of nodes.
A question related to that is, what are the sort of use cases that you think are really well suited for Kuzu?
So we did so the motivation to start Kuzu as a research project about the history of Kuzu is that before Kuzu, I had another research project called GraphFlow. And the way I entered into graph databases, as I said, during my PhD years, I was not really developing databases. We were developing MapReduce like distributed data processing systems. So I was in the graph vertical, but it wasn't a database. The reason I entered graph databases was because I had done as the first thing at University of Waterloo, my first study, a research project, was a user survey. It was a non-technical work. And we asked a bunch of sort of people who were using graph technology, different kinds of graph technologies, including RDF systems, property graph systems like Neo4j, people who were using Pregel-like systems, about sort of what are their challenges, what are they doing with these systems, what type of applications are they building, so on and so forth. So this was kind of like a survey in overall about 120 people. And one thing became very clear to us that people really liked property graph databases. They were kind of building applications on them. They were getting traction. That class of software was getting traction. The second thing was that people had major scalability and performance problems. So a lot of the work that we did in the previous project that I had called GraphFlow was to solve that problem. If we were to develop a modern graph database engine, what would it look like? What would its sort of query processor look like? What would its storage look like? What would its optimizer look like? So on, what would its indices look like? So on and so forth. So Kuzu, like a good application for Kuzu is if you're doing large graph analytics. So that's like the one case. A lot of our research, a lot of our expertise, a lot of the good ideas we're putting into Kuzu is based on many years of research we did in my group to answer that problem. How do we build a competent, fast graph database engine that is very good at finding graph patterns on large databases? So if you got essentially billions of records, billions of nodes, tens of billions of edges, and I think a very good use case for Kuzu is that our query processor is quite sophisticated and quite competent, and so will perform really well and will shine on those workloads. So that's one. And then we see a lot of, because of embeddability, we see a lot of use cases that emerge from sort of embeddability aspects of Kuzu. So one advantage of embeddable systems is that, like a system like Kuzu, you could put it into a lot of different places. You could put it into your Android applications. You could put it onto Amazon Lambda functions. So we see this advantage where you see people building a lot of applications where they're on actually architectures that we don't even fully understand. Like there's people who put it onto Amazon Lambda to do on-demand querying of some S3 Kuzu databases. So maybe they do build Kuzu databases in some other application, but they put those backups into S3. And then from time to time on demand, when they need to query, they spin off a Lambda function. And then they connect to this S3 Kuzu database, do a quick query, and do that. And those kind of sort of use cases are coming, not particularly because of our competence with query processing and whatnot, and not particularly because they're processing a lot of large graphs, but because we're embeddable and it's very easy to build applications with that. So the ease of useness is bringing us some use cases.
And that kind of goes back to that pedigree or that look at SQLite and DuckDB. Just by happenstance, the previous guest was Francis Perry from MotherDuck.
Oh yeah, okay.
DuckDB for that, and so we're seeing this trend of embedding. We're not going out to this much more big, complex framework or system that's out there in the ether. We're bringing it within that address space of the same process. And I didn't talk to her about this, but there's also this ability of, if you're sitting in the same address space and you're not a distributed system, you're now much faster. You're not having to do this RPC call from your client to wherever. It's same address space. You can use. It can be significantly faster, and that, I think, that will enable us to do some interesting things.
That's right. So we've got, for example, an ability to do zero copy data movements into Kuzu from another Python library. So suppose you're using pandas and you've got a Python script that's doing some analytics, and as part of it, you're using pandas to construct some data frame, right? So that's like some maybe pre-processing that you did, and now you want to do some graph querying. So you can, for example, directly call copy from and point to the variable that binds to the data frame in Kuzu in your Python script, and will directly read from the pandas data frame without zero copy. So you're not going to essentially, we can directly, because we're in the same address space, because that data frame is in the same kind of process, we can get a pointer to it and directly scan it. Then that compares a lot. I mean, that got a big performance advantage than writing it to say an external CSV file or a Parquet file, and then from there copying into Kuzu. You don't have to do that because we're in the same space. We've got this zero copy advantage. So that's an example of not what I'm saying. It's not just the RPC, but it's also you could even do sort of other advantages, performance advantages of being in the same address space as the application.
Yeah, that is interesting. What's exciting you about your roadmap right now?
So we are excited about several features that are coming up, hopefully in the first quarter of 2025. One thing Kuzu was not very advanced in was we didn't have, aside from the default indices we have, like we have an index on the primary keys on node tables, and we have an index on the relationships records. We did not have more, I could also go here. We did not have other indices. And many people were demanding us to build some indices to enable certain applications. So we are building a vector index, native vector index. I can't type, but a vector index. I don't. Maybe I'll just say it. We're writing a vector, building a vector index, an HNSW based vector index that is native. So we're not using a separate library for this, and it's going to be disk based and hopefully scalable. And it's actually based on several years of research that I did. So it's very well taught. So I'm very excited about that. So that will allow people to essentially build applications in the AI space where several people are kind of experimenting with Kuzu in these techniques that people are talking a lot about these days, like graph rag. So they want to have essentially some records that they model as a graph that maybe represents some of the information in their unstructured text, but converted into more structured format in the form of a graph. But they often use it in conjunction with a vector database because they also want to do a traditional RAG. And some people do hybrid RAG, so on and so forth. But that kind of forces people right now to use Kuzu in conjunction with another vector database. But once we have the vector index, hopefully we'll simplify their architectures. So that's exciting. We're also building a full text search index. So people were essentially demanding some of these more retrieval features to be integrated into Kuzu that we are doing with these indices. We're also releasing actually very soon. The dev version is out as we speak for people to try a WASM version of Kuzu, so that you can put Kuzu also in your browser directly. So that's going to be interesting to see. We've had several people actually build their own WASM versions of Kuzu. We didn't do it officially, and but there was some interest in that, and that's something, for example, DuckDB has done as well, and they got some applications that are running DuckDB in Kuzu. And then the last thing that is coming up is we're right now in Kuzu. This is a common feature of graph databases that Kuzu is lacking here. Is you can run off the shelf large graph analytics procedures directly in Cypher statements. So you could do, for example, in a system like Neo4j, directly call PageRank, which is not a computation you can express in Cypher, like matches and wheres and returns. It's a much more advanced computation, but it's a very convenient feature where you can just say run PageRank on my records because we're modeling the data as a set of nodes and relationships. This is possible, and it's a common feature. So we did not have that. So that's also coming up in the first quarter of 2025, and we're excited to make Kuzu more feature rich with these features in the short term.
So one thing I found interesting about Kuzu is you chose an MIT license for it. Not that that's bad. I was more curious why you chose MIT versus LGPL or even an Apache license.
Good question, and I don't have I'm not going to have a very satisfying answer here because this was a decision that fried my brain to try to understand all these licenses. So there was one thing we knew that we wanted to go pick a license that will sort of maximize adoption, that people will think less about. Again, we also, I should just say, like Kuzu started as an academic project, and when we open source, we were not a company. Like we became a company several months later than we open source. But when we were open sourcing, it's as a general principle in academia also, I pick a very permissive license for the rest of the software artifacts from my research group. But in this case, MIT specifically was because we just looked at several open source sources, specifically DuckDB, because I was following how DuckDB moved from an academic project into a much more seriously adopted and sort of much more serious software. And also now several companies are around DuckDB. So I had the ambition to say, maybe I can spin this off as well. And if I want to spin off, let me look at some of these software that became adopted. So I wanted to go for look at those, and then DuckDB and several others. I think I'd seen MIT being used, so I picked that. So that's really but then I read these licenses, and I trying to understand without the lawyer walking through them is difficult. So I was like, okay. Then comes a day where we say, okay, we're going to pick one license, and I think there was really two things we could pick: Apache or MIT, but we ended up with MIT basically.
It's always funny, the things that are the most difficult. It's, there's the joke about naming is one of the hardest things, and then apparently it's finding the right license for your software as well.
Yeah. I think naming is like that. You need to put a deadline to make a decision. Otherwise, like I just realized that I'm never going to make a very informed decision about like MIT or Apache. So an example at least kind of gives me a direction. Like, okay, like if I can say, okay, DuckDB is doing MIT, I'll do MIT as well. But I didn't really. It's easier. That's the level at which I made the decision.
Well, speaking of names, why did you choose the name Kuzu? And spoiler, it's at the bottom of the page, and I've never seen anybody else actually at the bottom of the page tell you what the name means.
Yeah. So Kuzu, the reason we picked Kuzu is we were the overall idea of picking a name was we wanted to pick a name from an ancient language. So I'm fascinated with human languages, and we looked at Sumerian. Sumerian is not spoken, but it's the oldest known human language. We looked at Tamil. Tamil is the oldest known spoken language still. And we looked at Greek and Chinese, and my co-founders are Chinese, and everybody proposed a set of things. So I think, I looked at this, there's a Sumerian dictionary, and I don't know how people actually know how these words are pronounced. And we were looking for a word related to knowledge overall. So we said, like, let's pick a word that's related to knowledge. We want to be associated with knowledge and knowledge graphs and some of these sort of concepts that also relate to the area that Kuzu is in as a graph database. And so there was this, one word in the Sumerian dictionary, Kuzu, and it means wisdom overall. I think it's bright and you can bright and to know, and it apparently means wisdom. So we ended up with that. It could have been what was it? There was a Tamil word that was very close. I forgot now, but Vidya or something. I forgot. It was another one that we liked. We just wanted to like the sound of it as well. And unfortunately, though, I should say, Kuzu means sheep in Turkish. And because I'm Turkish, everybody thinks I named it Kuzu because I'm Turkish. And I actually hesitated a lot to pick Kuzu because I knew people would kind of keep associating with this animal sheep. But that's not the reason. And anyways, so here we are. That's what we're sticking with. Again, that was another case where there's a deadline. We said, okay, today we're making the decision. Otherwise, you can take weeks to make such decisions.
Okay. That would be funny. You could have your logo be a sheep instead of the current one.
Maybe we'll move there. Yeah.
Yeah. you've made some difficult decisions. In fact, you kind of alluded to it just now. How do you make these difficult decisions?
Yeah, it's case by case. I think I like examples a lot. Like I want to see what others did, and so I am quite sort of a believer in experience. Like I believe in the value of experience. So if there is some hard decision that I'm going to make, I do make sure that I talk to somebody who's experienced, who's gone through this, and I am always sort of quite confident actually with my own instinct immediately if I'm facing a hard decision. So because like life has taught me, I guess that my first instincts, I'm always surprised at how naive they are, like generally. So I do believe in experience a lot. So I love finding people who've gone through very similar things and who'll just tell me this is what I did and this was the mistake, or this was good, this is what happened. So that is one thing I'll try to do a bit of due diligence in some of these hard decisions. Yeah.
How would you go through and, if you said you're not the greatest coder, how does not the greatest coder create something that's actually pretty technically difficult? But
Yeah.
we ran out of time for that.
Yeah.
You
I've
become a good manager, I guess.
Yeah, other people in the team are quite good in Kuzu in coding. Like I meet with I like doing the design. No one understands the system, I think, as much as I do. So putting modesty aside a bit, but like I do understand databases quite well, having been in the field for 15 years. Right, like my education, even though it wasn't on databases, like I was a database group though. It was a database lab. Like my advisor is a core database researcher. My committee members were core database researcher. I always published in databases. So I did end up knowing the system and the principles of database management systems are built very well. So I do a lot of technical work, but it's usually like in overall design and sort of suggesting sort of how to benchmark certain ways of implementing things and whatnot. And I'm slowly delegating. In the very beginning, I had a lot of fun coding for part-time for about a year and a half. When there was no one working on this, we were an academic project, and it was me and a master's student. During those times, to accelerate the speed of development a bit, I did. But no, like if you ask my co-founders or my ex-students, basically almost all of them, they don't particularly like my code. They're like, this is too verbose, because I write it like they can see that my instincts are more like on clarity and like making sure it's principled, and they're more hackers. They're like, no, it's just too much work. You don't need to do this. You could just take these shortcuts and whatnot. Then I take longer to review. I take longer to write, and it's too slow for them. So but I think the way you do it is, like obviously I'm not comparing myself to Mike Stonebreaker, but Mike Stonebreaker also doesn't code ever, and he's created maybe 7, 8, maybe 10 databases. And his students but he finds these students who are good coders, like Daniel Abadi, who built a C-Store, one of the first columnar systems in early 2000s or late 1990s. So he makes sure some of his students code, and he himself doesn't code. And then there's others like Peter Bones. I don't know if you know Peter. We probably mentioned this. Peter Bones is at MotherDuck right now. He was the advisor of Hannes, I think. It's DuckDB. He himself codes, and now at MotherDuck also he codes. Like he's gone to MotherDuck to code. So that's a different type of person who are developing systems. But yeah, that's my my skills, my kind of thing puts me in the situation where I'm better off trying to find people who can code better than me.
Well, Semih, thank you for coming on the show, talking about knowledge graphs. That was really interesting, very deeply technical, which I love. Thank you so much for sharing.
Thank you so much for having me, Jesse. It was a pleasure.